solution of YC.
Welcome
There's
everyone.
a particular solution. There's a
as a
complementary
continuation
solution.
on the lecture series of
Or someone would say the
fields.
homogeneous solution.
Let's look at what we
when
have
you
for
set
today.
the entire differential
You're looking at the
equation to
second
zero, and that's where you have the source term attached to it.
which is the derivatives and integrals.
Then when I'm done,
of
I can
vector
find my
fields.
general solution as
derivatives
the combination
and integrals
of
vector
YC
fields.
and YP.
In this video, I'm going to consider
But you know,
the
before you find the general
derivatives
solution, you would have
of the vector
done a differentiation of the YP to the highest order, and then you substitute, you compare
there's
coefficients.
derivatives and integrals.
I hope you remember this
kind of
techniques
vector fields,
or these steps.
which is
That's
for
the same thing we are going to
gradient
do
fields or
under
the
systems.
conservative fields.
We follow the same
We also
procedure,
have
just that
what we
now
call the
as a system
potential
of equation.
function to
So I
look
want to
out
go
for.
through my slides here
And then the
to make it
integrals
easier
is
for us to
looking at
understand.
the line integral.
Before I take an example,
So I call it
okay.
L.
So let's look at table 1. Now we want to
Forgive my
know how
shorthand,
these
but
guess functions are
makes life
obtained.
easier.
How do I obtain
So
these
gradient
guess
fields,
functions?
conservative fields, potential
And not
functions,
to
and line integrals.
have these
I'll
guess
be
functions for MOU.
Concentrating
There are some
on
special
the
cases of
derivative
our GT.
aspect for
The
now.
GT can be a
And then in the
polynomial.
subsequent ones, look at the
It can
other
be an exponential
integrals.
function. It can also be
So
a
we've already
cos and
established
then
the fact
sine
that
function.
Vector
Any
fields
of
are
these
fields
three
with
things or
vectors,
linear
and hence
combinations
we have magnitudes and then
Of these
directions.
cases, you are good to go.
Now let's look at the
So let me
gradient
take
fields
examples
or
from
the
the table.
conservative fields.
Assuming my
These are used
guess
to model physical
function.
systems in which energy is conserved. So as the name suggests, conservative fields, energy,
So assuming
let
my
me say
source
work done.
function G is of the form 1, 1.
is conserved.
What would be the YP?
Whatever you do, you still
Now
get
this is how I'll
whatever
take the
work
guess
energy
or the
you
YP.
had in the initial
Assuming
stage.
I have
So
just this
input is
point to
equal to
consider.
output. So let's look at the example.
You
of
know your
physical
YP is a
systems.
copy
We
of
have that
your
of the gravitational fields or
YC.
forces.
And there's a constant
that connect us
polynomial. Means
to
I'm
our
going to
world.
have
when
an
I'm
A.
on the planet Earth, there's no way I'm going to float.
Now because this is a
Gravity
system,
pulls
it
me
means
down.
I have 2 A.
Let's look at when
This
you
is
throw a
also
ball. If I'm throwing it up,
a
it will go
G20
up,
and I'll
gravity
have
will
under
just
A.
bring it down.
So I'll simply
We
write
can also
this
have an
as
example like
some
the
A1
electric
and
field,
A2.
which is regarding a
This would be
positive and
my
negatively
YP.
charged
In the second example,
fields.
so this is a
We can also
polynomial
look at the
case.
spring. If
If
I
I
have
have
an elastic
G
spring,
as
you can see from the image
Negative
if it's
1, 2, and
compressed
then
or it is
T.
stretched.
Realize
Whatever
that
you
this
do,
is
it
the
will
same
still
as
come back
writing
into
as
its
negative
original
T.
state. It means the
then
energy
2T.
is conserved.
If I'm taking
Or let me
this
say, use the
alone,
word it is reserved.
my
It is
guess
intact.
function would have
Nothing is
been reducing the
wasted
order. It would have
or
been
lost.
A.
So mathematically, how do I
In the same way, if I'm
express
taking this, it
conservative?
would have still been AT plus B.
We are talking
But
about
because it's a
of a
system,
vector field.
it
So I
means
have
I'm
a
going to
vector
get some
field F.
a big A
If I can find
times T
some
times
gradient
plus
of another
the big
function,
B.
that's a small f. So
And
that's
this
a
is going to
capital
be
F.
A1,
The gradient of a
A2,
small function.
taking the T,
If these relations
and
are
then
equal,
B1, B2.
then I'm saying that I have the gradient field.
So I'm
or
showing
the
a
field is
schematic of getting
conserved.
the guess functions.
Energy
This
done
to a polynomial. If I have a
is
trig
the
function,
same.
it's a
And
3
so what
to
I know my big F is a
exponential
vector field. So what is small f?
3t.
Small f is what we call the potential
If I take this
function.
as 1, I have 3e 3t, and I have 2e 3t. If I'm
And this
considering
is
just this
the
aspect
what
of
we
the
need. So
dt,
this number
realize that your
formula
guess
here is
function
for
would
the
have been some
gradient of which we've done
3t.
gradient.
So because
Since
it's
a
2
multi-calculus, it's going to
it
be a
means I
partial
have
derivatives.
a1, a2.
So
So I'm adding this
let's
one
look at
to
what
it.
this one means.
Exponential 3t.
This means I
This will
have a
simply be
gradient
my
of
guess function.
f respect to x. If I'm in 3D, I. That means I'm using the
The
unit
last one,
vector field.
If I'm taking
F respect to
a cos,
yj.
say
F
2,
respect to z.
3
If I'm 2
cos
it
t.
become f to the power I, and then that of y to the respect to
Again,
j.
this is the
I
same as
can
2
rewrite
cos
this
t,
as fx
3 cos t.
fy.
If I'm considering just this one, I would have set my gt as a copy, so that would be some a.
approach.
Don't forget, if it's a cos, we add what the
for
sine
vector
function,
fields.
b sine
Don't
t.
forget your small f is
So
a
because
potential
there are 2,
field.
it means I'll
The
have
question
this
is, we
as
always
some
know the vector field.
a1,
So
a2,
how
taking
do
the
we
cos part,
determine
plus
the potential
the b1 b2 taking the
or the
sign part.
potential function.
So if this
What
was
is
a
the
3
potential function?
let's say there's a
That is
negative
my
1 here,
next
I would have
agenda. But in
I would have
this,
said
we have
a1
two scenarios
a2
to
a3
consider.
and
The
then
first
b1
is when
b2
assuming
b3.
f is given
This would have been the
and you want to
simple guess
verify
functions.
that it's
And so you don't
your
be
field
scared
is
if you are
conserved or
solving
not.
system of
second case,
equations
f
with the
is not
method of undetermined
given.
coefficient.
And you
On
want
that
to find
note,
it.
let's take a quick example here.
So let's take the first case.
Let me move to the
Assuming
next
we
sheet.
know the function given,
We
want
want
to
to
verify
find a
that it's
solution to a
indeed a
system
potential
given as,
function.
I want to
to
change the
the vector
notations
field.
here. Let's say 1 y
Let me
prime
take a
equal
next
to
sheet.
x1 plus 2x2
So example
plus
1.
3t.
We
And
are
then
given
x2 prime
the
is equal
vector
to
field big F is equal
2x1 plus x2
to this function.
plus 2. So it means I'm just changing my x to be x1 and then y to be x2. That's because throughout the videos I'm using x1s and x2s, not to confuse anyone. I would like to extend my write-up here since I
So
wouldn't
this
be
is
in
three
need of the
dimension. It
slides.
means it has
Let's see
x,
what happens.
y, and then z.
Now
And
this
it's
is the
my
system.
potential function.
So
given
one,
here
what
is
do? I
given as
write my matrix form.
x squared y z.
The matrix form for this is some x1 prime, x2 prime is
Okay.
equal to
You want
the
to
coefficient
establish that
1,
this is a
2,
potential fit.
2, 1.
Is it a potential
plus-
function?
No,
How do we
multiplying,
verify that?
sorry.
It says that if I can find the gradient
Those
of the
would have been
potential
multiplying the
function
unknowns
such
x1,
that it's equal
x2
to the vector
plus
field,
the source term. In
then
this case, there's a source
f
term
is
here,
indeed a potential function.
which
So
is
let's
this two
verify that.
guys.
What is the gradient of f?
It's not equal to 0.
It means I'm finding f respect to
They're the
x
ones without the unknown
and f
functions.
respect to y and then f respect to z. So
Two.
let's do that.
Now, because it's
What do I get
non-homogeneous, what do we
respect
do? We
to
have
x?
to
This
solve for the
partial
homogeneous
derivative because there's a
solution.
multiple
It means
variable.
I'm having
X
some
respect
x
to
prime
x, I'm going to
minus
get
ax equal to 0.
2x
I'm assuming the source
y
term
z
here is 0.
minus y
Before you
equals
go into
f.
solving homogeneous, what do you
This
do?
fx.
You have to find the
F respect to
eigenvalues
y. I'm going to get
or the roots,
x squared
and that is giving us a
minus
minus lambda I is
x
equal to 0. So it means my concentration is just
x
on the
y.
a.
f respect
That
to
is
z.
1 minus lambda 2.
And that is giving me
2 here, 1 minus lambda
just
equal to 0.
2x
If you should
y.
expand this,
Sorry,
you are going to get,
it's giving me x squared y. Now you compare this
you're going to get the eigenvalues to be
your
that 1 minus
big
lambda all square
F1.
minus 4.
f
And the eigenvalues will be
then f
3 and
component.
then
I did the
negative
same.
1. Anywhere
did
you
the same.
position
Let's
this, you are
compare.
good to go.
From the question f1
So that is my eigenvalues. The fourth thing to do is
So let
after
me
finding
extend
eigenvalues,
this,
you know we have to find
part of the
eigenvectors.
sheet.
Because these are matrices. So I'll find the
From
two
the question,
eigenvectors.
f1 was given us
So I'll first take when lambda is equal to 3 and when lambda is equal to
Sorry for
negative
that.
1.
is 2
If it's 3, I'm going to have
y z
negative 2
minus
to,
some y
to
cos x
negative
y.
2.
You realize it's
Some
the
v1,
same.
v2 equal to some
F2
0, 0. I'm sure
is
by
given
now
as
you've been
x
able to
square
solve
y
eigenvectors. So I'll
minus
go
some
ahead and
x
just write
cos
the final
x y. This
answer.
also equal.
If I'm taking
And then the
negative 1, I'm
last
going
term
to
is
get
x square y. This is
2,
equal.
2,
So since
2,
my
some
gradient
v1,
of the small
v2
f is equal to big
0,
F, it
0.
means that f is indeed a potential.
And for here, the eigenvectors
function.
for at lambda
would
equal to 3,
conserve the field.
we are supposed to get,
So that's how simple you verify
let me see what
it.
I worked out here.
Okay. Now let's look at the smart guesses here.
You're going to get
let's assume that
v1 to
example
be
two. What is
1,
the vector field? You
1.
must be able to differentiate the vector
And
fields
at
from the
negative 1,
potential
your
function
v2 is
given.
going to be
Vector fields are given as
negative 1, 1. You can
or they're
confirm or
given in
verify
this
that.
angle bracket. So realize that my vector field is given as
So that is my
means the first
eigenvalue.
one is 2,
Sorry, my eigenvectors.
2x
So I can write
cos
the
y
general solution for the homogeneous
second
part. So I'm going to
big
say
F. The
x
second part is
c
given as
complementary solution. Some
um,
c1 v1 that plus
2y
c2
z squared.
v2,
And then the third part
and there's the same
is
as
given as just
c1
y squared.
1 1
And then my functions, the small
negative
f is
e3t
given as
plus
x squared
c2
cos y
the eigenvector
plus y squared z
e
squared.
negative
So I want
t.
to first find the
This is my
derivative
complementary
x
solution,
and
as simple
compare.
as that. These are real and distinct. The
You
root
realize
here
that
is
with
real and
respect to x, I'm going to
distinct,
get
so you don't
2x
forget that.
cos yx. The last term go to 0. If I differentiate f respect to y, I'm getting
Okay. If it's a complex root, then you know how to write the solution. If it's repeated, you know how to write the solution. Right. So the
sin
sixth
yz
step.
plus
Now to find my particular solution, it says it's a copy
over
of
here. Immediately
the
I get
GT.
to know that this is not
The
even
question: what is my
equal to that.
GT?
So I want to go ahead and
GT
find
is
the
the
last
same
term,
as 3t
f of z,
and
I'm
then
going
2.
to get some y.
And what is my
x
guess
squared
function? If I'm considering, you realize that there's a polynomial.
Differentiate cos, you're going to get negative sign.
There's also a polynomial,
yz,
but there's of
plus
degree 0, this
some
degree 1. So I take the
squared.
highest
degree,
degree, which is on this
so
one.
even right
If I'm writing just
I've moved
a
to find
yp for such,
the next term.
I'm going to say this
So you realize
at
that
plus b.
indeed this
And
is
so because
not
I have two values, I have two of this,
potential function,
my gt is going to
because the
be
gradient of the small f is
some
not equal
a1
to
a2
the
times the
vector
t.
field. The
So
last
a will
example,
break down to what? A1 a2, and then b takes,
so I have my solution
B1,
as no, it is not a
and
potential
b breaks
function.
down to
The
this.
last example, I have my small f
So
given
I'm
as
taking the highest degree polynomial to write my
over
gt.
2
Now let's look at the
minus y squared
checklist.
over 2. Let me find the
Do
derivative.
you see
What is the first
yp
derivative
in any
respect to
form
x?
of the
I'm going to
complementary
get
solution?
2x
So it means we are comparing,
minus 0. So this
we are
equal
comparing this
to xy.
to that.
The second derivative,
Do you see
I'm going
anything
to
of
get
that form?
some s squared on 2.
The answer is big no.
on 2. That's equal
So it means
to
our guess
s
solution
from 2
is good
minus
to
y.
use.
Okay, so I compare them.
Now what do we do? So
What is
the
the
next
first
step,
vector field?
forget about the
Whether it
labelling
is
of the
x,
steps.
y.
It's just to help you know
What's the
what you are
second
doing at
vector
this stage.
field?
What do? We
It
have
is
to now
s squared
differentiate
on
and
2
substitute.
minus y.
So we
Are they the
differentiate
same? Yes.
yp,
So
in this
I've
case
proven, I've
xp,
verified the
and
potential
substitute,
function such that the
and then
gradient of the small
compare
f is equal to the
coefficients.
vector field.
So we are going to do all
Hence,
three at
this
a go.
is a potential function, and that's how you
Let me
simply
rewrite my
verify
equation.
that.
Now
So
don't
the
forget
answer is
your
yes, it's a potential
differential equation was
function.
given as
And the
this.
example 3, that
ax
leads you to
equals
the
to
next
the
video.
gt.
That's the second case.
So I have to
Where
differentiate
your vector field is
the
given,
xp and substitute here.
but the potential function is not given to verify.
So what is my xp?
How do
xp
you
was
then
given
solve
as
for the potential function
a1
and then verify if
a2
it's
t,
indeed a potential function?
and then the
So I'll
other
take a
part
next
b1
video on
b2.
that.
How many times do I want to differentiate this?